Make a recording. All right, so our purpose is to show several problems to be NP complete. So as we said last time, so we're going to look at 4 problems. The first one is a bounded halting, and then we're going to look at bounded tiling. So bounded tiling is sometimes called Levin's theorem, and then we are going to look at satisfiability, Cook's theorem, and 3 SAT. So that's Cobb's theorem. Okay, so those are the problems we're going to look at. Of course, there are thousands of NP complete problems, so we can only touch a few of those to just get some ideas. And then we move on to approximation algorithms. Okay, so last time we started talking about halting problem, Turing machine halting problem. So this is a general. So this is an unbounded version. So to refresh your memory, so let's look at what this Turing machine halting problem is and why it is undecidable. And undecidable is also called unsolvable. Okay, so we defined H. So here we define H, which is a set of items. So each of these items or set of objects, each of these objects takes an encoding of a Turing machine and an input to that Turing machine. So hence this encoding, you can think of it as an integer or a binary string. You can think of this. So this is an encoding under a fixed encoding method. For instance, you may simply use ASCII code to convert any description of a Turing machine into a binary string. And this X is the input to M. You can also convert that into a binary string. So you think of this as a binary string. So you can think of this encoding as a binary string, or you can also think of it as an integer, because any binary string, you just put a 1 in front of it, it becomes an integer. So then what this mean? What this set H says that we have these encoding in this set, which are positive instances when M is a Turing machine and M on this X halts. Okay, so then this is not decidable. So decidable, so just to refresh your memory, decidability means that I have a language is decidable if there is a Turing machine such that on any X or any input, this Turing machine always halts. And when it halts, it will either end up as an accept state or a reject state. So if it's accept state, then this input belongs to this language. Otherwise, it doesn't belong to it. Okay, so that's what decidability means. So you use a Turing machine. Now think of Turing machine as a program or as an algorithm. It always halts, right? No matter what input you have, it always stops. And when it always stops, when it stops, it gives you an answer, whether that input belongs to this language or not. So then this H is not decidable. Of course, we know that to prove that H is not decidable, we can simply use a diagonalization. So let me just, again, this is to refresh your memory. So let's start a whiteboard here. Where was my whiteboard? What is this? Something's wrong here. So I have to stop sharing and start over again. All right. Okay, so first of all, to show that Turing machine halting problem H is not decidable. So the classic proof is as follows. So we use diagonalization by diagonalization. So first we list all possible Turing machines, right? So each Turing machine has a finite description. So under the fixed encoding, it corresponds to an integer. So that means all the Turing machines are countably many, so we can list them all. So we simply let M1, M2, blah, 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 be an enumeration of all Turing machines. So let's use shorthand for this. Okay, so again, this under a fixed encoding. So that means that when I have an integer, I can decode it. I can decode that integer back to a description of a Turing machine. Okay, so the proof that H is not decidable then is first we assume, right? So by contradiction, so assume H is decidable by a decider, SAD. So as I said earlier, so decider is a Turing machine that on input X, it always halts, and when it halts, it gives you a answer whether this input X belongs to H or not. So of course, now we construct a Turing machine. Let's call it DTM. Let's call it M. Okay, such that on input I, so let's call it just I as a integer. You think of it as a binary string. Okay, and on input I, it run D. Now D is a decider on MI I, so on this input. Okay, so which means that because all the Turing machine can be enumerated, so on any input, I can just take mi has that Turing machine, and then I let mi runs I. So D will give me an answer, right? So D always holds and gives me an answer. So if D accepts then M rejects I. Okay, and if D rejects, then M accepts I. Okay. So that's this construction of M. Now, this is a description of M, right? So this is an algorithm. Think of it as a program. So this is what this program does. So this is an algorithm. That's what I simulate D, and D gives me an answer. If D says accept this input, then I am going to reject I. Otherwise, if D says it rejects this input, then I'm going to accept I. Now, this M is a Turing machine. That means there is a J, an index J, such that M is MJ, because this is the enumeration for all Turing machines. So M is a Turing machine, so that means they must have some J such that M is equal to MJ. So now let's see. So now we are going to go see MJ, right? So let's say if J is accepted by MJ, so this really means if and only if. So if it's accept, so this is M, now this is M, right? So accepts it. If and only if D rejects it, that means that if and only if, now it says D rejects MJJ. So when D rejects it, it really means that MJ rejects, oops, MJ rejects J. Okay, so now here it says that J is accepted by MJ if and only if MJ rejects J. So this is a contradiction. So contradiction then indicates that your assumption that H is decidable. So this is wrong. So that means H is not decidable. So this is a diagonalization. So why is it that a diagonalization? Because this is what so I'm going to start anew. So this is what I'm looking at. So you have this M1, M2. So there's infinitely many Turing machines. All of the Turing machines are here. And then you look at your input one, all possible inputs, 1, 2, 3, and so on. So what I'm going to do here is that I'm looking at is a diagonal. So I want to know whether M1 accepts 1 and M2 accepts 2, right? Or M3 accepts 3. So that's why it is called diagonalization. Okay, so this is just to refresh your memory. Now we are going to see here, and move back. Okay, so one of the things I want to make a comment here is that if you ask any question about a Turing machine, right, whether this Turing machine accepts a particular input or Turing machine would do certain things, they anything you ask about Turing machine, it's undecidable because the simple thing, whether it's halting or not, it's undecidable, right? So if you do any other things, of course, it must halt first, right? So that means that there are many different problems about Turing machines. They are not decidable or unsolvable. But then the question here is that, Turing machine is a man-made device, and you're looking at these problems about a man-made device, so they are not natural. Okay, so by natural means that you want something that's not related to, or this something independent of these machines, right? So to refresh your memory, the first problem that's natural, that's undecidable, is called post-correspondence problem, right? But nevertheless, we can look into this concept that age actually is the hardest problem. So this halting problem is actually, even though it's very simple, right? Just want to know whether it halts or not. It is the hardest problem. And now this age is Turing acceptable because you can have a universal Turing machine that takes in this input. Just keep running M on X. If M accepts X, it will stop, right? So that is Turing acceptable. So it is the hardest problem in the class of Turing acceptable languages, okay? So that is the things that I want to point that one out. So it is the hardest problem in, well, Turing acceptable languages are also called recursively enumerable. So let me just use RE languages. Recursively enumerable. Okay, so it is the hardest. That means that any recursively enumerable language can be reduced to this halting problem. Okay, hence it is the hardest. Okay, so the proof is straightforward. So here's a proof. I don't need to start a whiteboard. It's straightforward. So let A be any Turing acceptable language. Okay, then that means by definition, there is a Turing machine, let's call it MA, such that MA accepts A. So then we're going to construct a reduction. Now again, this reduction doesn't need to be polynomial time computable. As a matter of fact, it could be, but right now we don't have. We just say this f of x is computable, right? So what this f of x is, just take the encoding of this Turing machine, MA, and an x. Right? So any encoding is polynomial time computable. So it is a polynomial time computable function, reduction actually. But in this case, we just say that it is computable. So this reduction, this is a reduction because for any x, x is in A, okay, if and only if MA, so this Turing machine MA halts on X because A is Turing acceptable. So it means that there is a machine. If it's in A, then it halts. If it's not in A, then we don't know, right? So it may not halt at all, or even if it halts, it rejects the input. So, but if it's in A, then this MA accepts, MA halts on X, so that means that f of X is in H. Okay, so this is straightforward. So now because of this, it motivates us to think about a bounded halting problem in the setting of time-bounded computation. Okay, so now let's look at this problem here. So the instance of this problem is a non-deterministic Turing machine M, a binary string X, and a unitary notion 0 to the n, representing positive integer n. So which means that I have this encoding M X 0 to the n. So this just indicates that this is integer n. So for the purpose that the size of this 0 to the n is just n, okay? So that's the purpose. So, so then we want to know whether M accepts X in n steps. Okay, so that's a decidable problem. We want to know on this input mx0 to the n, whether M accepts X in n steps. So this problem is NP complete. Okay. So why is it NP complete? So we first look, we can see that this problem is in NP because this Turing machine M here is could be non-deterministic. So it accepts it. So that means you guess a path and then you verify to see whether that path actually ends at an accept state in n steps. Okay. In other words, that path, the length of that path is n, at most n. Right? So. Okay, so now we let BH, bounded halting, be the set of these instances, three things, M, X, and 0 to the n. And the property is that M accepts X in n steps, and then BH is NP complete. So then we use the same reduction as before, but now we are going to reduce every problem in NP to BH. Okay, so first of all, we look at the length of this input. So the length will be the description of M and X and N. So description of M, of course, you use this notation, and this is the X, and because we use a unitary notion 0 to the n, so this is just so it's n. So we're gonna construct a reduction. Reduce every, so for every language A in NP, we're gonna reduce A to BH, okay? So again, this is pretty straightforward because A is in NP, that means, by definition, there is a non-deterministic Turing machine MA, such that MA accepts A in P time, okay? So this is a P of n time, so this is a polynomial. P of n time, n is the length of the input. Okay, or we can say it as in P of length of x. Okay, for on any input x. So then the reduction is just this. So you compare to the reduction we talked about earlier. So what we did here is just add this component, so 0 to the P of length of x. So it is a reduction because for any x, x is in A, by definition, if and only if MA accepts x in P of length of x steps, then by definition, that means you put these three things together, that's in BH. Okay, so it is a reduction. Hence, BH is NP complete. So you may wonder why such a thing so simple would be the hardest problem in NP, because So it's just that if you're given a non-deterministic Turing machine, and then you are given an X, you want to know whether this M actually accepts this input in a bounded number of steps. Okay, and that time bound is part of your input. Then this problem is actually the hardest problem. But as before, it is not natural. So this problem is not natural in the sense that it is dependent of Turing machines. And Turing machine is a man-made device. Hence, people want to know, okay, can we have can we have a natural problems, okay, that are independent of machines? Okay, so then the first problem we're going to look at is bounded timing. Oops. Okay, yeah. Okay, so what's a bounded timing? So first, let's look at what does it mean by tiling. So tiling is, so let me open up a whiteboard here. So tiling just means that you are given a set of tiles. By tiles, of course, we mean it's a square tile. So you got a finite set. So this is finite set of tiles, and this is actually a tile types. Okay, so which means that for each, you have a finite set of types, but for each type, you can have unlimited tiles. All right, so then so each of these tiles on each edge has a color, right? So we can say this is A, color B, color B, C, color D. So each edge has a color. Then what you want to do is you want to say whether you can use these tiles to completely fill in a given space. So what does that mean? It means that the adjacent tiles, so let's say I put this tile A, B, D, C, and then if I can put another tile here, so that means that they are adjacent edge, so the edge has to have the same color. Okay, so that means if I can tile these things, completely fill in the space, then they must have the same color. Okay, so that's what is tiling means. Now this is the unbounded tiling. We know that unbounded tiling is also not decidable, but if we put a time bound there, then we have a bounded tiling. So now let's go back to the definition here. So what we are having here now is a finite set of tile types, and then we are given a n by n square. And then we want to know, okay, whether we can extend these tiles and fill in this n by n square. So that means that we need to arrange n square tiles to cover the square so that the symbols or the colors on the common size of adjacent tiles are the same. Okay, so now let's look at this bounded tiling problem. So in instance, first you have a finite set of tiles. And as before, we have a unitary notation 0 to the n, representing positive integer n. And also you are given a sequence of tiles, S. So this is sequence. So each small si is a tile, and si and si plus 1, they match each other, which means that the symbols on the adjacent edges, on these common edges of adjacent tiles are the same. Okay, so then we want to know whether we can pick tiles from T, capital T, to extend this initial sequence to cover an n by n square or n by n space. So that's our space. So this is a question, yeah. Can S be extended to tile and n by n square using tiles from T? Okay. And this is...
Professor, a quick question. Is expected that the tiles only match on the left and right side or on all sides?
Say it again.
So the adjacent tiles should match, right? Only on the left and right side or on all sides?
Only on the common edge. Is that what you're asking? So if you can put the tiles here, so this is a common edge, they have to be the same.
Right.
If
so if there's a tile
here,
above, if
yeah,
there's a
this
tile
is a common, yeah.
Yeah, okay. All right, thanks.
Yeah. Okay, so now let's see why it is NP complete. Okay, so now we define this, so we put all the positive incidences. Positive means that it can be extended, okay? So to tile and n by n square. So this problem is NP complete. Okay, so the first of all, that this BT in NP, it can be verified as follows, so which means that you want to see whether there is such a tiling. So basically, when you prove something in NP, it basically means that you're given a solution, then it's very easy to verify that solution is indeed a legal solution. Okay, but then finding a solution may not be easy. So here, I want to know whether this is NP. If you are given, if you are telling me and saying that, okay, this is a tiling, okay, so you give me this tile, so I just need to check to see whether the common edge of adjacent tiles they have the same color, so that's easy to verify. So it is in NP. And second, we are going to show that we are going to reduce any problem A in NP to bounded timing. So that's what we are going to do. So then we can say that BT is NP complete. So the idea then is we are going to use tiles to represent a computation history of a Turing machine on input X. This is sort of similar to the post correspondence problem. Okay, so now because A is in NP, that means by definition there is a non-deterministic Turing machine MA. So now let's put this Turing machine here. So we get finite set of states. Okay, a finite set of alphabet. So this includes the input alphabet and the tape alphabet. And we have a transition function. And the transition function is in the following form, which you take a state. And this is not a halting state. And then you map to a to a new state, and I'm sorry, there's a symbol here. Let me put, so this sigma, you will go to Q sigma, and then you can either move left or move to right. Because it is non-deterministic, I may have more than one choice, so actually it is going to a power set. So I put a power set 2 to the this thing to indicate I have multiple choices. So that's a transition, and HA is a halting, there's accepting halting state, and HR is a rejecting halting state. So that is what is Turing machine MA accepts A. So now we are going to construct tiles to represent a computation history of this Turing machine. So computation history is just from one configuration to the next, to the next, to the next, until it reaches a halting state. Okay, so that is a history, right? So that, again, to refresh your memory. All right. So now how do we do this? Now we will just look at each transition. So we first look at this too. Okay. So I have a transition. So this is a so this transition will move to the right. Okay. So you have on current state Q on current input symbol alpha, you go to a new state P, rewrite alpha to beta and move to R. So now how do I use tiles to represent this move? So here I'm going to put stay on the right here. And this is Q alpha. Okay, and then this alpha will be rewritten to beta. Okay, so, and then I'm going to say, okay, so this P changes to, I'm sorry, this is Q here. So Q will change to P. And so this will be P. So in other words, you will think of configurations like this. So we have Q alpha and gamma. So gamma would be the next symbol after alpha. Okay, so there may be some symbols here, but at this point, this Q, the rewrite head points to alpha here. Okay, so then the next one, so we change to P. Alpha is changed. I'm sorry, P is moved to right. So let me change this. Okay, alpha becomes beta, and Q becomes P and move to right. So now this position of the head points to gamma, but the state is P. So then we are going to duplicate this using a tile. So that means now I'm going to have P gamma on top. So this is where you begin with, and this is where you end up with. Beta P gamma, and this Q alpha gamma. I want this to be on the right of P, so now I'm going to put P here. So this indicates that these two can be put adjacent to each other. When I put this we don't specify anything, that means it's blank. So we use a blank B, so we don't have to specify that. It's a particular color, right? So it's a blank. So that's a transition. So any transition you have like this, you're going to create tiles like this. And similarly for the left ones. So again, what we are having here is Q alpha, let's say this gamma here. Because now we're going to move to the left, so we're going to put something on here. So Q now, alpha is changed to beta, same thing. Okay, but then you are going to move to the left, so that means your next state P, the head actually now points to gamma. So how do I do this? So again, where I begin with Q alpha, and then alpha change to beta. And then the next one would be, okay, so this is gamma, and this is P gamma. But this guy has to be put on the right of this guy because you move to the left. So then I'm going to put P here. And then I'm going to put P there. So that way I can put these things on the right of it. So that's what it is. So the rest of it, I can duplicate any symbol up. Okay, so this is duplicating any symbol up. And this means that if I reach a halting, I reach a step state, I can also duplicate this up. Okay. And then these are special ones for the initial sequence. Okay, so initial sequence just means that this has to be on the lower left corner. Okay, so I have this, so it has to be on the lower left corner because there isn't anything that can match these dollar signs. And this will be at the bottom because there isn't anything on top of it has a dollar sign, so it has to be on the bottom. All right, so and then on the side, it's except this, the first one, because initially our configuration is a Q0 for any input is X1, X2, up to Xn. Each Xi is a symbol. So what I represent this thing will be $, okay, and then there's a Q0X1, pound, and then pound, $, this will be X2, right? So the last one is $ here, pound, pound, Xn. So they can be matched. So this represents the initial configuration. So then, as you can see, I can use these tiles to represent a computation history from the initial configuration, following the transition, then you move to the next configuration, you move to the next, you move to the next, until you reach a accept state, then you can duplicate up. And if you reach a reject state, then you can only stop there. So that means now I just need to make my say this MA is a time bound PA of, so this is a polynomial time bound, right? So then we just need to make my square larger than PA. So this, my N would be larger. So this is the idea here. Let me start a new whiteboard. Okay, so I just need to make it. So this is, so let's say this is a Q polynomial. So let me use a polynomial here. P, just say PA prime. PA prime, so PA prime is greater than PA. So then you can duplicate, so this is a initial configuration, you can duplicate this one up. At a certain point, H, if it accepts, that means that HA is reached, then that tiles can be duplicated up. Any other tiles can also be duplicated up because we have this, right? So you can always duplicate up. So that means I can tile the entire square if and only if HA is reached. If HR is reached somewhere, because before, so at a certain point, PA is reached, and this HR is reached, then you have no way to extend this HR because there isn't any such tile there to cover the entire square. Okay, so that is the proof. All right, so you can read the slides for the formal writing, but the idea is what I just said. All right. Okay, so bounded timing is NP complete. This was first proven by Levin, so we sometimes call it a Levin's theorem. It's not hard, but this is important from the historical point of view because this is started in late 1960s and early 1970s. People were puzzled why there were so many problems in applications, and people tried very hard to find polynomial time algorithms, but they failed. And then people started to look into this, and they found out that some problems that look pretty straightforward, but they're still very hard. Okay, so bounded timing is NP complete. Okay, so this is the
Okay.
Yeah, hello?
Oh, I'm sorry. I thought I wasn't mute.
Okay. All right, so now let's look at the next one. That's Cook's theorem. He published a paper in 1972. So I remember I read his paper when I was in undergrad. So that was, I think I read it in 1978 or something, or 1980. I don't remember, but at that time it was considered a breaking news, right? So because that the Boolean satisfiability, people use it a lot in writing programs, right? Or conditional statements. You must have a Boolean formula to indicate a condition. So if you have a Boolean formula, I just ask a simple question, whether this Boolean formula has a truth assignment to make it true. And this is very hard. So even to answer this question is NP complete. Okay, so now let's see why it is the case. So first, we're going to look at Boolean formulas in a particular form. We call it a conjunctive normal form. So conjunctive normal form is just like this. You have a bunch of literals. Okay, so there's a concept here. So literal is a variable or a negation of a variable. So it's a literal is a variable or a negation of a variable. So this negation, sometimes we put a little bar on top of it. Okay, so then your conjunctive normal form is like this. You have a bunch of literal. Okay. So let's say this is the eyes clause. You have M1 many. Okay, and then you n another clause. So let's call it J1 or J2 or JM2. We call it MI here, MJ here. Okay, so then N. So in other words, each formula in conjunctive normal form of n variables is given as a set of clauses. Okay, so each clause CI is a set of literals, and to form a Boolean formula, you just take the I think it's called conjunction, right? Or, right? So each clause is, so this is a clause. Okay, and so we sometimes use a plus to indicate its clause, and we use product to indicate conjunction, and, okay, and. So, and also we use 1 for true, 0 for false. Okay, so that will make sense now, right? So we can just use plus for or. We use multiplication for and. So so that is what this form looks like. So each conjunctive normal form Boolean formula is in this form. Okay, so now you are given an F like this, and you want to know whether F is satisfiable, and this problem is NP complete. So, so now let's look at this description of the problem. So instance is a Boolean formula psi in conjunctive normal form. Question is psi satisfiable? Okay, so we put all the positive instances into this set called SAT set. Then we say that set is NP complete. And then we want to see why it is the case. Okay, Cook's theorem. SAT is NP complete. Okay, so not the SAT that every high school student needs to take. It's not that SAT.
Some think it's NP complete.
What?
Though some students think that SAT is NP complete too.
Yeah, that's right? Okay. All right. So what we're going to do is to reduce bounded timing to SAT. Now remember, bounded timing is NP complete. So if we can reduce a NP complete problem to a new problem, that new problem is also NP complete because the reduction is transitive. So now we're going to reduce bounded timing to SAT. Okay, so then first, let's look at an instance of bounded timing is this. Is T as 0 to the n. And then we are going to use a Boolean formula to represent tiling process. Okay, so that's the idea, right? So we use, so as you can see, we use tiling to represent computational history of Turing machines. And now we're going to use a Boolean formula to represent legal tiling. Okay, so that's basically what the idea is. So now we label the different tiles occurred in S. This is the initial initial sequence of tiles. So we label them as T1 up to TL, and the tiles in T, but not in S, as TL plus 1 up to T sub length of T. So then we use it to construct a Boolean formula. So, and then we let H sub T denote the set of tile pairs, TI, TJ, such that TI can be placed horizontally left to TJ. So that means I have, so this is TI, I can put TJ on the right of TI. So if that is legal, so if this is legal, then these two tiles will be placed in HT. Likewise, I can put vertical. So, so the VT. Okay, so which is a, so it says that TI can be placed vertically below TJ. So that means TJ is here, TI is here. So if it's legal, then we place these two tiles in VT. So now we're going to construct Boolean formulas. First, we're going to construct, so we're going to represent, we use the variables, okay? So how many variables? So now let's look at, so this is my n by n square. So then for you have n square many tiles, and for many cells. For each cell, you have up to this many tiles you can place in it. So that means now I need to represent all possible cases, right? So that means I need these many variables, n squared times the length of t. And I'm going to call them Vij, K. So this is Vij for location. So the i's row, j's column, and k is for the k's tile, because you have this many tiles, so we already labeled them from T1 up to T sub T. So then I can have these many variables to represent all possible tiling on this square. And then what I need to do now is to come up with Boolean formula to represent legal tiling, right? Legal tiling. Okay, so later we are going to set Vijk to be 1 if that particular cell is tiled by the case tile, or is covered by the case tile. Okay, so that's how we are going to set that truth assignment. So this is a truth assignment. The meaning is that for that particular cell, and I have that TK occupy, I have TK in that tile. So then we are going to construct a formula to represent a legal tiling. So now we're going to do, so this formula psi is broken into 3 sub-formulas, side 1, side 2, side 3. So we're going to see what each of these means. Okay. Okay. So the first one, so we represent the initial timing. So initial sequence of tiles you are given is, let's say, is capital S, which is S1 up to XM. So this is your input. So assume that Sj is equal to Tkj. That means the Kj's tile. So what we are going to say here is that because those tiles from 1, right? So this is the bottom. Let's say my index is like this. Okay, so this is the bottom one. And this is N. So then this tile, 1, 1 will be tiled by TK1. So this is TK2 and so on up to here. Okay, so that is psi 1. And so psi 1 is equal to 1 if and only if the J cell in the bottom row is covered by TKJ. So that represents the initial sequence of tiles. And so this is psi 1. So psi 2 is going to represent horizontally legal and vertically legal. So you have further two things. So this is horizontal. This is horizontal. This is vertical. Okay. So now we represent this tiling. So then for each tile type, K and K prime, where they cannot be placed in HT, they cannot be they cannot be placed adjacent to each other horizontally. So that's what we're going to say that. Now remember, you have these two. So let's say this is IJ. So this is IJ. Then this is IJ plus 1. If you put TK here, then you cannot put TK prime there because they cannot be placed in each other. So which means that you take the negation of them. If you can put TK here, TK prime here, because I know that I cannot allow this to happen, so I take a negation. So this is and, this and that. Negation means that either negation of this or negation of that. So that's what this means. Okay, so for all these tiles that cannot be in HT, so we take the product because they have to be true at the same time, right? So also for all the I and J, for all cells, they have to be true. So vertical is similar. So then you put these two together, it indicates that, so you put them together, indicates that psi 2 is equal to 1 if and only if the adjacency conditions of tiling are satisfied. So that's what that means. And then the last one, we want to make sure each cell is occupied by exactly one tile. Okay, you cannot have more than one, and you cannot have any, right? You must be tiled by exactly one. So that's the last sub-formula to indicate. So this means for them to be true, so that means that each cell must have at least one tile, and this indicates that they can have just one tile, right? So put them together. Then we know that the tiling instances is positive if and only if I have a truth assignment to make this Boolean formula true. Okay, so that is the proof. Now, the reason I presented this proof is that it is much simpler than almost any proof you see from any textbook, okay, because they are very long. And this is actually pretty straightforward, but I took bounded timing first. Okay. So last, I have 10 minutes. Yeah, 10 minutes is enough, so I can finish this. So the last one is 3 SAT. Okay. So 3 SAT, it was proven by Karp. Of course, Karp later published a paper. In that paper, he actually proved 6 classic problems to be NP complete. So this was one of them. So that's why we cannot just call this one Karp's theorem, because he has so many. So this is just a restricted version of SAT by restricting the number of literals in each clause to be exactly 3. Okay, so so this is 3 CNF. So its input is a particular Boolean formula in conjunctive normal form, such that each clause has exactly 3 literals. Then we want to know whether this is satisfiable, this Boolean formula is satisfiable. So what we are going to do is to reduce SAT to 3 SAT. So here is the proof. Again, I'm going to present a much simpler proof here than what you have in your textbook. Okay. So 3 SAT is NP complete. So we're going to reduce SAT to 3 SAT. So here is the proof. Move too much. Okay. So first, we are going to introduce, now let's say for any F, it has its formula, but on top of it, so it has its variables. Okay, so you may have its variables on top of F's variables. We are going to introduce 3 new variables. Okay, so which means that they are different from F's original variables. We call them Y1, Y2, Y3, and then we are going to include these 7 new clauses. So what are these? It's just all possible cases except the last one. Okay, so you can see here is Y1, Y2, Y3, except, so you can think of this as you make them true, there's 1, 1, 1, right? So 1, 1, 0. So then you have 2 to the 3, that's equal to 8 many, but then I don't have this. The last one I don't have. This when Y1, Y2, Y3 are all zeros. So this is excluded. That's it. So that means now that's a good thing. So I put all of them in here. If my formula is true, okay, if and only if Y1, Y2, Y3 has to be set to 1. Okay, satisfy all these. So all these 7 clauses are true only exactly when Y1, Y2, Y3 is equal to 1. So that makes our proof easier. Okay. So now we are going to use a case analysis, okay, to reduce each clause in F to a set of 3 clauses. Okay. So the case 1 would be K is equal to 1. So let's say this is so this is an arbitrary clause in F. So this K is the number of literals. So then, of course, k, the first case is k is equal to 1. So then we simply replace this clause by z1 negation y1 negation y2. Now remember, for all these 7 clauses to be true, all y1, y2, y3 had to be set to 1. So that means that these two are set false. So this set false, that means z1 has to be true. So that means that it's equivalent, right? So this c then is equivalent to this. Likewise, if k is equal to 2, I keep z1 and z2, and I add negation y1 in it. Or you can also add negation y2. It doesn't matter, because this c then is equivalent to this new clause. When k is equal to 3, do nothing. When k is equal to 4, this is what we're going to do here. So k is equal to 4 means that I have z1, z2, z3, z4. I'm going to break them into 2 parts. Okay, and then I'm going to introduce a new variable u1 and replace c by the following 3 clauses. So these 2, as you can see here, so z1, z3, z4, then you have a u1 and then negation of a u1. So that means that if this is true, then it has to be false, and vice versa. And then I'm going to negate 3, include u1, and put a negation y1. Now this is 0. This is 0. Okay. So you can prove, you can do a prove yourself that these construction. So C is true if and only if. So C has a truth assignment if and only if all these 4 clauses has truth assignment. Because, as I said here, that this is Z3 plus Z4 is equivalent to U1, and Z1 plus Z2 plus U1 then is equivalent to this. So that's what this clause is. Okay, so the last 3 clauses is equivalent to this. The last 3 clauses implies this. So then for k plus 4, greater than 4, we do an induction. So we inductively apply case 4 until only clauses of 3 literals left, right? So your k is equal to 5, you first get down to 4, clauses of 4, and then you get down to clauses of 3. Okay, so that is the proof. So I have presented new proofs for these problems to be NP complete. They are simpler, easier to read, I hope, than those in your textbook. So I have 1 minute left. Any question? Okay, so that will be the end of NP completeness. And next time we are going to look at approximation algorithms. So I'm going to call an end for today's class, and see you next week.
Thanks. See you next week.
Yeah.
Thank you. Bye-bye.
Yeah, bye-bye.
Hi, Professor. I was just curious.
Yeah, hi.
For the material on approximation algorithms, are we going to touch upon any approximate solutions to TSP?
Yeah.
Awesome. Okay. Cool.
Uh-huh. Yeah,
Thank you.
that's on my slide. Yes.
Okay, just looking forward to it. Thanks.
But not the best one though. Because the best one is very hard to look at, but the standard one, let me just say it that way.
Okay, roger that.
Yeah.
Thank you.
Okay.